Good morning. I'm very happy to be here with you today at the Korea Supercomputing Conference, and I'm sorry all of us can't be there in person with you. My name is Katie Antypas. I'm a Division Deputy at NERSC, the National Energy Research Scientific Computing Facility at Lawrence Berkeley National Lab. And recently, I took a leadership position in the United States Department of Energy-sponsored Exascale computing project, also known as ECP. Today, I'm going to be talking with you about the Exascale computing project, and in particular, about the area which I now lead called hardware and integration. So without further ado, I'm going to share my screen here and get started. Oh, okay. And yes, let's get started. So the Department of Energy Exascale Computing Initiative is made up of 3 components, of which the Exascale Computing Project is just one. The other parts of the Exascale Computing Initiative are the deployment of Exascale systems. There will be 3 initially at the OLC, at the Oak Ridge Leadership Computing Facility, the Argonne Leadership Computing Facility, and at Livermore, Lawrence Livermore National Lab. There's also select program and office application development in a number of specific applications. One of the things that sometimes people get confused about with the Exascale computing project is that the deployment of the systems is actually outside the project, and the Exascale computing project is focusing on preparing applications and software for the Exascale systems. There are really 4 key objectives and goals as part of the Exascale computing project. One is to ensure that these Exascale systems really can deliver mission-critical applications. We know that deploying applications can be really challenging, and so we know that we must prepare applications and not just simply deliver hardware. The Exascale computing project also has a goal to deliver a really long-term and sustainable software ecosystem for these Exascale platforms. A goal of the Exascale computing project is to promote the health of the US computing industry and to maintain US leadership in high-performance computing. So let's take a look at some of the numbers behind ECP. It's a 7-year project for $1.8 billion of research and development that was launched in 2016. Nearly all of the national laboratories in the Department of Energy are taking some part in the project. There's 6 key laboratories that are really spearheading the leadership of the effort. And as I mentioned before, there's 3 technical areas: application development, software technology, and hardware integration, which is what the area that I lead. And there's more than 80 researchers, 80 research and development teams, and over 1,000 researchers that are funded under the Exascale computing project. Now let's take a look at the roadmap to the Exascale systems. So let's start on the right of the chart, and you can see the 3 Exascale systems that will be delivered in the 2021 timeframe in the Office of Science. This is the Frontier system for Oak Ridge National Lab. This system will have AMD GPUs. The next system on the list here is the Aurora system. Aurora will be delivered to Argonne National Lab, and this is an Intel-based system which will use Intel GPUs. And the El Capitan system will come a year or so later to Livermore and also use AMD GPUs. So my own home laboratory is Berkeley Lab, and we will be deploying a pre-Exascale system later this year called Perlmutter. And so Perlmutter will include NVIDIA A100 GPUs, as well as the AMD CPUs. Now, we can look at the hardware landscape and how this has changed. If you look back into the 2018 era with Summit and Sierra, we were really looking at just one type of GPU available on these systems in the HPC market in the US, and that was through NVIDIA. So the hardware environment has really diversified since that time. So our effort in the Exascale computing project is to prepare applications and software to run on these Exascale era platforms that I've just described. There are three main technical areas in the Exascale computing project. The first is application development, and the goal of application development is to really enhance and develop the predictive capability of DOE's applications. So there's 24 applications, which I'll talk about more in the next slide. The second area is software and technology. And the goal of this area is to deliver a really robust and integrated software stack to the Exascale systems. And finally, there's hardware and integration, the area I lead, which is a diverse set of sub-projects that includes both hardware integration as well as application optimization and software deployment and training. Let's take a closer look at the ECP, the Exascale Computing Project applications. You can see there's a range of application domains that are supported under the ECP project, from energy security, scientific discovery, earth and environmental science, healthcare, and national security. There's 24 applications, and they span 10 of the Department of Energy program offices, as well as the NIH, the National Institutes of Health. Now let's take a look at the ECP software technology area. And you can see the software that is being supported in the Exascale computing project covers a wide range of areas as well, from programming models and runtimes, development tools, math libraries, visualization, and I/O, as well as we call the software ecosystem. So the tools that are needed to develop and deploy software to the Exascale systems. Here's a deeper look at some of the ST products. And you can see just how many there are, first of all, and how many different areas they cover. And so you can see the different color-coded categories here from the legend. So visualization and data are in this purple, whereas math libraries are in blue. And our idea and goal is to release these software packages as an ensemble together, as a package, so that they are tested together and that they work in concert on the Exascale systems. And this effort to deploy, test, and release the software as a bundle is called what we're calling E4S. So it's Extreme Scale Scientific Software Stack. And it's a SPAC-based distribution of the software technology products. And they're tested for interoperability and portability between multiple architectures. You can see the E4S software deployment stack has had a number of releases every few months. And we are very excited about getting this really coherent and well-tested stack onto the Exascale and pre-Exascale systems. So let's talk about our strategy for preparing applications and software to run on the Exascale systems. We know that in order to run on this advanced hardware, applications will need to change. They will need to new algorithms and methods. They'll need to scale to really unprecedented levels and find on-node parallelism. So these applications are going to need lots of attention and effort, and we want there to be a real deep partnership with the facilities. And when I say the facilities, I mean facilities like NERSC, facilities like the Oak Ridge Leadership Computing Facility and the Argonne Leadership Computing Facility. And so without that engagement from the facilities and the vendors, these exascale applications could be unprepared. So instead, we want a very tight partnership with the facilities. And so this includes early training of scientists and application developers. We have what we call hackathons, so they're deep dives with vendors who are experts in compiler technologies or their particular architecture. And we have deep engagements with the vendors through centers of excellence. And we are also deploying early hardware so that the applications and the software technology teams can gain early experience to the hardware before the exascale systems come online. All right, well, let me tell you a little bit more specifically about the hardware and integration area within the Exascale computing project. As I mentioned before, there are a number of different areas under the hardware and integration area, which I lead. And this includes hardware innovations and evaluation, application integration, software deployment, and training, outreach, and getting allocations for these teams at the facilities. We have a very experienced team in hardware and integration, which you'll see, excuse me, abbreviated as HI. So Susan Coughlin is the Deputy Director of the hardware and integration area, and she brings a wealth of experience deploying, acquiring, and managing systems. Bronis Desupinski leads our Path Forward effort. Scott Pakin leads hardware evaluation. Judy Hill leads application integration at the facilities. Ryan Adamson, software deployment. Haritha Sidiba-Thuni-Som, facility resource utilization, that's allocations. And Ashley Barker leads our productivity and training area. Let's look at these 6 areas in more detail. So the path forward element is an area that has been critical for early vendor hardware R&D and the goal is to invest in multiple exascale capable technologies. Hardware evaluation looks closely at system architectures and system hardware and determines how those system designs could be used to inform facilities and ECP. Application integration is focused on preparing applications to be able to be ported and optimized to the exascale and pre-exascale systems. Software deployment is focused on deploying the E4S stack, that is the software technologies that are developed as part of the Exascale computing project, onto the Exascale platforms. And that looks at how we test software and deploy it in production. Facility resource utilization is about making sure that the ECP times have allocations on these facilities. And training and productivity is a very wide area that looks at lessons learned, best practices, and delivers seminars, hackathons, and other training sessions to the Exascale computing project teams. Now, underlying all of these areas are deep engagements with the high-performance computing facilities within the Department of Energy. Let's take a deeper look at each of these. The first is Path Forward. And so in 2017, Path Forward funded 6 companies on the right, labeled there: AMD Cray, which is now part of HPE, HPE individually, IBM, Intel, and NVIDIA. And they were given 3-year contracts that will end pretty shortly here in December of 2020. In aggregate, the contracts were valued at over $260 million. And what we can say is that many of the technologies that were funded under the Path Forward effort and developed will be featured in the Exascale systems. And this includes node architectures, interconnects, as well as I/O capabilities and subsystems. The Path Forward team is leadership team is shown here. And it's been a great group of people to work with. And as I mentioned before, the Path Forward element will be coming to a close here at the end of the year, which makes sense because we have, now we're going to be deploying these systems. The next area to take a look at is hardware evaluation. And the goal is really to answer key questions about hardware alternatives and performance. So the hardware evaluation team answers questions such as, is it worth it to port this application to GPUs? What does this new hardware feature outweigh the expense at this point? And the hardware evaluation team is also, the work is coming to a close pretty soon, again, because the Exascale platforms are being launched. There's 3 areas under hardware evaluation: memory technologies, analytical modeling, and interconnect simulations. And you can see some of the recent examples of some of their findings listed there below. Software deployment at the facilities is really about delivering a software stack to the Exascale platforms so that the application development teams can use it. We will also be supporting testing and deployment of the software stack. And the next slide has an image of that here. So when you look at how we deploy software right now in HPC systems, at least the HPC systems I've been a part of, we're deploying software. Typically we use modules, and often that software isn't always tested as a bundle, even though we know that many of our applications need many packages and many libraries. And so too often it's really left to the user to determine the compatibility and interoperability of different packages. So in order to increase the productivity of our teams, our goal is really to test our software and always be testing the latest build. We'll call it the experimental branch or the latest build. And once that experimental build has been tested and checked off on, and it passes all of the tests, then we could choose to deploy it into production. In the meantime, so that production instance will be stable, while in the meantime, we will continue to deploy, we'll continue to test the experimental version of the software package. Okay, so here's a little animation that just shows how we expect to be able to deploy software onto these systems. So let's move on to the next area, which is application integration at the facilities. This is a really, really important part of hardware integration because we know that these application teams need deep partnerships with the facilities and hardware vendors in order to be able to optimize applications for these systems. So all of the application teams are partnered within a liaison at one of the 3 facilities within the Office of Science. This is the Argonne Leadership Computing Facility for Aurora, led by Catherine Riley, the Frontier System at the OLCF, led by Judy Hill, and then on the pre-exascale Perlmutter system at NERSC, and the lead there is Debbie Bard. And so each application team has a liaison at the facility who helps work with the application team to optimize and prepare the application for the new architecture. So these applications face many common challenges. They could have flat performance profiles. They need to improve strong scaling. They really need to understand how their application will perform on accelerators. Many of them had not been using accelerators in the past. They have challenges in the choice of programming model that they want to use and the trade-offs between portability or directly programming in a vendor programming model. It's important that they be able to select the mathematical models that fit their science and architecture, and then they have to deal with many, many software dependencies. So let's take a look at one of the application integration highlights. This comes from the Exalt project that has been partnered with a liaison at NERSC, whose name is Raul. And so what the team has done is really improve the performance of the Snap kernel. And so the graph that you can see on the right, the x-axis is time, and then the y-axis shows the increase in speed that the team has been able to get through different hackathons and different partnerships with the vendors. The second highlight that I would like to call out is from the Frontier project, with Exastar as the application. And so Exastar is really a multi-physics AMR-based toolkit for simulating stellar explosions, supernovae, neutron stars, and mergers. And this is a coupled physics code and has many, many lines of code. And so the application liaison, in this case, Austin Harris, has been looking at how to speed up the code for the Frontier architecture. And you can see here that compared to the CPU implementation has seen really significant speed ups, nearly 100x speed up relative to single core, and has been working on optimizing to GPU port using OpenMP offload, which is what something a number of our applications, a programming model, a number of our applications are looking at using for these exascale systems. Finally, the last area I wanted to mention here is our training and productivity area. This is really a key part of the whole exascale computing project. And we really could not prepare such a large group of applications and software technology teams without this robust effort. And so this effort includes webinars and deep dive workshops, lectures, hackathons, and tutorials. And the goal of this effort is really to build up the expertise in the community, share lessons learned, and to develop, promote, and high productivity tools and languages that will improve the overall ECP Exascale software and application environment. A component of the training and productivity area is really focusing on improving the productivity and sustainability of scientific software. And so the team has put out a couple of reports on this area on how to improve scientific software. There's a Better Scientific Software site. And as I mentioned before, we're going to be releasing the E4S Exascale software environment really as a package that's been tested on a number of these platforms. And this has been an area where I think there's been lots of improvement and lots of ideas generated in how we can make the software environment more sustainable. In terms of the number of trainings that have been held so far to date in the Exascale computing projects, there's been over 100 and over 4,000 participants to date. And I think it's been one of the most successful parts of the Exascale computing initiative is that at the end of this project, we'll have a whole host of scientists, engineers, postdocs, and students who have been trained on the latest technologies, applications, software, and architectures. So in summary, I wanted to talk a little bit about how we measure success in ECP. We're putting a lot of effort into preparing these applications, developing a software environment, enriching the hardware ecosystem. And so there's a question on how do we know if we were successful? And so in the Exascale computing project, we're looking at 4 key criteria that I'll just go over quickly here. The first is that we're looking at the performance improvement of mission critical applications. So every application has a different way of measuring how quickly it ran. It could simply be wall clock time, or it could be looking at the number of iterations per second or some other metric that makes sense in a particular science domain. And so the threshold, or what we would say is the minimum bar that we want to hit, is that at least 50% of the applications in this category, which is about half of the 24, would achieve this an improvement of their figure of merit by more than 50%. Whereas the objective, or kind of this, what we call the stretch goal, was that 100% of their applications achieve their stretch goal. A second criteria we look at as far as the success of ECP is to broaden the reach of the Exascale science and mission capability. And so there are, as I mentioned, about half of the applications are in this other category. And the goal for these applications, which in many cases are newer to HPC, is that half of them can run and execute their challenge problem on the Exascale systems. And then the objective, or the stretch goal, is that all of them can. We're also looking for a productive and sustainable software ecosystem. And so this success criteria is around the ST products and the E4S software suite. And so we're looking for over 50% of the teams to meet their goals for software impact, which includes teams that are using their product, as application teams that are using their product, as well as the ability to run on multiple Exascale systems. And then there's a goal to really enrich the hardware ecosystem. And so this criteria is around the vendors that we're funded under the Path Forward system to meet 80% of all the Path Forward milestones. I'm happy to report we've actually already met that and are nearing the objective of 100% completion. So in summary, the Exascale computing project is pushing forward the development of applications, the software ecosystem for the Exascale computing environment, and the hardware and integration area is delivering these applications and software technology and integrating them to the Exascale environment. That's all I have prepared for you today. I wish I could take some questions. I'd be happy to answer any questions that I received by email. And I really hope that you have a great and successful conference here today. Thank you.